Okay, so let's prove this theorem. It says if f has a local extrema at x equals c, so what does that mean? It means that the y value at c is bigger than or equal to the y values anywhere else. Okay, we saw some examples where you could have two y values be the same, so they'll both be local extrema, but this y value has to be at least as big as all others. Okay, and this is true when x is near c, because it's local. Okay? And it also assumes that f is differentiable at c, so that means f prime of c exists. It can be calculated. All right, we're going to try to prove that this has to be true. All right, so what do we know here? Let's draw a picture. There's going to be a point c, and there's going to be a y value at point c, and there's a function that has a local maximum there at c. And we're going to look at both sides of c and see what happens. So let's first look at case 1. Case 1 is x is bigger than c. So we're going to say x is here. And this would be f of x, right? And that could be anywhere on this curve. And then we'll do case 2 after that, and then we're going to combine the cases for our result. So the case 2 will be when x is less than c. Okay, so what do we know? We know that f of c is greater than or equal to f of x. We can subtract f of c from both sides and say that f of x minus f of c is greater than or equal to 0. If x is bigger than c, then that means x minus c has to be more than 0, which means I can divide both sides of this inequality by x minus c, and that's okay because I'm dividing by a positive number. So I'll have 0 because I'm still dividing 0 by a positive number, still 0. And over here I'll have f of x minus f of c over x minus c. And I hope that looks familiar to you. Okay, that's f of x minus f of a over x minus a. That's the definition of derivative if I add a limit. So what limit do I need to add? I need to add the limit as x approaches c. And this limit has to exist because this is the definition of f prime of c. And by hypothesis of the theorem, that derivative exists. So what do we have? We have 0 is greater than or equal to f prime of c. Okay, that doesn't prove what we want yet, so let's keep going. Case 2 said that x had to be less than c. We still have that f of c is greater than or equal to f of x. Sorry, I was going to jump ahead of myself. Okay, greater than or equal to f of x. Okay, let's do the same thing. Let's subtract f of c from both sides. X is less than c, then x minus c is less than 0. It's a negative. So if I divide both sides by x minus c, I have to flip the inequality sign. It's one of my pre-cal awkward rules, but it's true. So this becomes what I wanted it to be like last time, but I had to flip the inequality sign. Okay, we'll do the limit thing again, and that limit has to exist because f is differentiable at c. So now you have 0 is less than or equal to f primed at c. Now, look at what you've got. You're saying that a number f prime of c is less than or equal to 0 and also greater than or equal to 0. So the only way those two statements can both be true is if f prime is exactly equal to 0 at c. So there's the conclusion of the proof. And if you wanted to do it for a minimum, it'd be very similar to that structure right there.